In this video series, we will cover the lessons in Elegoo's Arduino Starter Kit. The controller board we will be using is the MEGA2560 Rev 3. You may already have a different Arduino board, but you can still follow along. The pin connections are identical and other kits use the same components. You can check out the user manual if you want a detailed comparison, but the functionality is pretty much the same. To start using the controller, we need an Integrated Development Environment, or IDE for short. An IDE is basically a software application for programmers to write, compile, and test code. In our case, we need the Arduino IDE. On Arduino's official website, download the software for your computer's operating system. Just run the installer after it's finished downloading. You will be prompted for which user to make the software available. Let's proceed with the default setup. Setup is complete, and now we have a way to communicate with the controller and give it code to execute. On the next lesson, we'll look at libraries. What are libraries and how do we install them? Before we proceed with the next lesson, let's check out some settings where you can change stuff like theme and file location. Go to File and Preferences. You can also use the shortcut key Ctrl+, Here you can change things like theme, font size, and the sketchbook location where to save our sketches. Anyway, these settings are optional. You can leave this unchanged. A sketch is what we call the program we write for Arduino in this IDE. A sketch file is saved with a .ini extension. We already have one open here, a blank sketch. We'll talk about this more as we go on. In this lesson, we'll talk about libraries. When you connect a component or module like a sensor or a display to the controller, you need a low-level code to communicate with it. Instead of writing this low-level code yourself, you would use a library, a pre-written code you include at the top of your sketch. The sketch is the main script telling Arduino what to do, and the library is included or added to make it easier to work with components. Think of a library as a toolbox full of reusable tools your sketch can use. To add a library, go to Sketch, Include Library, Manage Libraries, or Ctrl+Shift+I for shortcut. You can also just click the library icon on the left panel. Let's try adding the audio library. You can see here the earlier versions, and if you want more info, this will open the docs on your browser. Click Install and wait until a notification shows up on the lower right. You can now add this to your sketch so you can play audio files from a memory card using an SD card module. Now let's look at the serial monitor. Navigate to Tools, then look for Serial Monitor, or you can press Ctrl+Shift+M. A new window will open. We can use this for debugging, monitoring data, sending commands to Arduino, and communicating with other devices. We don't have a controller connected, so we can't do anything with it for now. We'll go ahead and connect our Mega controller. If we go to Tools, then Port, we can now see that the controller is connected. We can then select to use it from the drop-down. The controller is ready to receive and execute instructions. We can test this by uploading a simple sketch that will print a message in the serial monitor. On this blank sketch, we have two functions. The first function runs once when Arduino is powered on or reset. The second function runs repeatedly in a loop, and it will run until Arduino is turned off. Let's put our initial code inside the first function. This will start communication between Arduino and the computer. The next line will print a message to the serial monitor. On the second function, it will check if there is data coming from the serial monitor. 0 if we haven't typed and entered any data. If we do, this condition is met and the data entered will be stored to a variable named input. On the third line, it will send back the message you typed plus the value of the variable input, which is the text we entered. Let's save this sketch, verify if there's no error, and then upload it to the board. Here we can see the message from the first function. We'll type and enter some text to see if the loop function is working. Looks like everything is working. We can see the message being sent back to the monitor. You might notice in the serial monitor these weird characters. Sometimes this happens after uploading a new sketch due to residual data from the bootloader or timing issues during the initial serial communication. We can add a delay in the setup function before any serial print statement to allow Arduino to fully initialize. Let's clear the serial monitor and upload the updated sketch. The weird characters are gone and we can see our code still working. Before we proceed to the next lesson, let's quickly touch on baud rate. On the upper right corner of the serial monitor, there's a drop-down with different numbers. This is the speed of communication measured in bits per second or BPS. 9600 baud means Arduino sends or receives data at 9600 BPS. This value should be the same to what we set for communication at the start of our sketch. Different values will lead to gibberish data. Lower values mean slower, but more stable, good for beginners and simple projects. Higher value is faster for sending lots of data like GPS, but is more sensitive to noise, especially with long cables. For these lessons, we'll stick with the default value. And that's it for this lesson. See you on the next one. In this lesson, we'll learn how to control the built-in LED and our MEGA controller board. In the previous lesson, you might notice when we connected the board that one of the LED, which is labeled L, is already blinking. The boards are generally shipped with a blink sketch pre-installed. We will reprogram the board with our edited sketch. A collection of example sketches are included in Arduino IDE. Let's load up one by going to File, Examples, Basics, and then Blink. A new sketch window will open. These examples are read-only. We can upload them to the board as it is, but since we will be changing it, we need to save our own copy. From the File menu, let's save it as MyBlink. It is now accessible from Sketchbook and also in the recent sketches. Before we proceed, let's check in Tools that the correct board and port is selected. The board and port information is also displayed at the bottom right of the IDE. Let's take a look at the sketch and make a quick rundown on what it does. In the setup function, we have a line that tells Arduino that the onboard LED will be used as an output and we'll be sending signals to it. In the loop function, the first two lines will turn the LED on by sending 5 volts to its pin and then pause the program, keeping the LED on for 1 second. The next line will repeat the same instruction, but this time it will send 0 volts, turning the LED off for 1 second. As long as the board has power, this code will repeat and keep the LED blinking. By the way, these grayed out texts are not part of the executable code. These are notes or comments written by developers, usually explaining what the code does. You can add a comment by enclosing it or using these symbols. Now we'll go ahead and upload the sketch to the board. Observe the LED and try to recognize the blink timing. Let's change the delay to 500. The LED will now be half a second on and half a second off. Let's reduce it to half again. Now the LED is blinking twice per second. And that's it for this simple lesson. See you again on the next one. In this lesson, we'll start connecting other components to the board. We will be using the controller, the breadboard, a 5mm LED, resistors with different values, and some jumper wires. Our goal is to turn the LED on with 3 different brightness. We'll utilize 2 pins from the board to supply power, a 5-volt pin and a ground pin. As we proceed with the assembly, we'll talk about each component's function. The breadboard is used for testing circuits without soldering. In these holes, you can insert the pins like jumper wire to make a temporary connection. Underneath this plastic are just metal strips. What's important to remember is which pinholes connect to each other. Here's the layout of the metal strips underneath. There are also some markings to help you trace connections. Let's take the first component to connect to our breadboard. This is a resistor, which from the name itself resists the flow of electricity. We'll use 3 of these with different ohm values. Ohm is the unit of resistance shortened to the Greek letter omega. You can check the resistance value of a resistor by its colored stripes, or you can use a multimeter. Resistors doesn't have a polarity or a positive-negative lead, so you can connect it either way. Let's connect all 3 resistors, one end in the positive terminal of the breadboard and one end in the short row of pinholes. You can use the positive and negative terminal interchangeably, but it may get confusing for complex circuits. The pinholes used here are spaced apart just for clarity, but you can use any row of pinholes you want. Let's move on to LED. Unlike resistor, the LED has a positive and negative lead. It will not turn on if the polarity is incorrect. The longer lead or pin is positive. There's also a flat edge on the body side of the negative lead. We'll insert the longer, positive lead along the 5-hole pin rows to connect to one end of the resistor, and the shorter negative lead along the negative power rails or terminal. Now we just need to connect the jumper wire to complete the circuit. Take the black wire and insert it along the negative power rail. Then the red wire along the positive power rail. Plug in the controller, look for the ground pinhole and insert the black wire. Then insert the red wire in the 5-volt pinhole. The first resistor has a value of 220 ohms. As we go to higher resistance with 1K and 10K ohms, the LED brightness decreases. What if we don't use any resistor and just connect the LED directly to the 5-volt pin? The LED will instantly burn due to excessive current. A typical 5mm LED has a forward current of 10 to 20 milliamps. Without the resistor, it will draw as much current as it can, causing it to overheat and damage its internal components. I've mentioned earlier that we can use the power rail interchangeably, so let's try swapping the wire connection. The LED doesn't light because the polarity was reversed. Let's fix the LED pin connection. It's working again, but now the resistor is on the other side. It still works because unlike the LED, the resistor is non-polar. In this lesson, we'll do a similar exercise lighting LED, but instead of a single color, we'll use RGB. We need a controller, breadboard, 3 220 ohm resistors, jumper wires, and the RGB LED. We've talked about these components already, except the RGB LED. The RGB LED produces different colors by combining the three individual colors, red, green, and blue, each having different brightness. Essentially, the RGB LED is 3 LED in one package. If we are to manually mix our own RGB LED, we will use different resistor values like what we did in the previous lesson. But that is a lot of work. The MEGA controller has a function to output a variable amount of power to each pin designated to each color. The RGB LED has 4 leads, 3 positive leads we call anode, 1 for each color, and a single negative lead we call cathode. The negative lead or cathode is the longest of the 4. It's the second pin from the edge with a flat portion. We'll connect this pin to the ground pinhole of the controller. To supply power and adjust the brightness of the RGB LED, we'll use the board's built-in PWM pins. PWM, short for pulse width modulation, is used to control the amount of power by rapidly switching the supply voltage on and off at a certain frequency. It's an efficient way of powering electronic devices. Let's start building the circuit and connect this RGB LED. I'll connect the components spaced apart as much as I can just to make the connections easier to see. You can use any row of pins you want. We'll connect the resistors next. Remember, there's no positive or negative side. Connect the wires starting with the red anode. Cathode with black ground wire, the green anode, and lastly blue anode. To finish the circuit, connect the wires to the controller. Insert the black wire to the ground pin hole. Red wire to pin 6, green wire to pin 5, and blue wire to pin 3. Let's head over now to Arduino IDE and set up the sketch to control the supply of power to the circuit. In the support files included with the CD, look for the RGB LED sketch. These files are also available to download from Elegoo website. We won't be going over too much detail on the programming side of Arduino. It should have a dedicated course of its own. But for us to get the idea, we'll simply discuss what the code does or how it works. The first 3 lines of code defines the name or assigns the pin number to the corresponding color name of the LED anode. Color names are easier to remember and makes the code easier to read. We've used pin 3 for blue, pin 5 for green, and pin 6 for red. The pin numbers seem random, but in most Arduino boards, these are PWM pins. In our case with MEGA, we can use any of the PWM pins labeled on the board. In the setup function, the first 3 lines tells Arduino those pins will send signals, not receive. The last 3 lines sets red LED on at high or full, while the green and blue LED at low or off. After the setup function, we have declared variables that will hold brightness values for each color. This will range from 0, equivalent to LED being off, and 255 at full brightness. Inside the loop function, we have a delay time set to 10 milliseconds to make the fade of each color transition smooth. In the next 3 lines, a brightness value is assigned to the variables declared earlier. Red is at full brightness, green and blue is at 0 brightness. This will be the starting color of the LED. Next, we have a for statement that decreases the red value by 1 while increasing the green value. This will repeat 255 times until the red value reaches down to 0 and the green value reaches up to 255. The blue value is not changed and still at the initial 0 value. At this point, the LED has finished its transition from red to green. The variables are then updated and will be the starting value for the next for statement. Now it's green to blue transition, and the last for statement from blue going back to red, and then it goes in infinite loop. Let's upload this sketch and see what happens to the LED. We can see it light up starting at red, then transitions to green, to blue, and back to red. Another way to think of this is, every 10 milliseconds, Arduino turns on the 3 LED at different brightness, producing different colors each time. Each step happens so fast that if we remove the 10 milliseconds delay, our eyes cannot perceive the transition from one color to another. Let's try this and remove the delay or replace the value to 0. We cannot see the transition. The LED just appears to be white. Let's set it back to 10. And that concludes our lesson. Next, we'll introduce digital inputs. In this lesson, we'll learn how to control an LED using push buttons with digital input. We need the controller, breadboard, a 220 ohm resistor, a 5mm LED, and some jumper wires. In addition, we'll use 2 push buttons as switches. These are simple components that connect 2 contacts together when pressed, allowing electricity to flow through them. We'll get back to these switches. For now, let's build the circuit starting with the 5mm LED. Remember, with a single color LED, the longer lead is the positive. We'll insert the pins with its positive on the right. Next, connect the 220 ohm resistor to the positive end of the LED. Now back to the switches. There are 4 pins in these switches, but there are only 2 electrical connections. The partner pins to use are those 2 connected on one side of the body. Whichever side is okay. The pins are also spaced in a way that will fit when inserted along the center divider. When not oriented properly, those pins will not align with the pinholes. Connect them with a little space in between. Now let's connect the jumper wire from the LED's negative terminal to the negative power rail. We'll also connect one pin from both switches. Then a jumper wire to connect it all to the controller. The remaining colored wires are for the other end of the switches and for the positive end of the LED connected to the resistor. To connect to the controller, black wire goes in the ground pin, blue and yellow to pin 9 and 8. Lastly, red wire to pin 5. You may see the LED fading on and off. This behavior is from the sketch of the previous lesson. Head over to the code folder and look for the sketch file for digital inputs. Let's take a quick look at the code and see what it does. First, variables are declared and assigned each a pin number. You can use other pins in the board, just update these numbers to match. This next line can be deleted. We won't be using this. You can comment it out or just ignore it for now. In the setup function, pin 5 with the red wire is set as an output to control the LED. We can set a high or low signal to turn the LED on or off. Pin 9 and 8 for button A and B with the blue and yellow wire are set as an input with pull-up resistor. This sets the pin status to high when the button is not pressed. In the loop function, we have an if statement. If button A at pin 9 is pressed, it makes a connection to ground, changing the pin status from high to low. When Arduino detects this change, it sends a high signal 5 volts to pin 5, turning the LED on. The same logic is applied to button B at pin 8, except a low signal 0 volt is sent to pin 5, turning the LED off. We can now upload this and see if it works. Pressing button A turns the LED on, while pressing button B turns it off. It is working as intended. We already get the circuit working. This additional work is just optional. You can move on to the next lesson at this point. Let's do some testing and swap the wires and use the other side of the switches. We'll also make some changes in the sketch. First, we've added const, meaning constant, to our variables just to make it clear that these values never change. We removed the unused line of code, shortened variable names, and in the loop function, instead of using two if statements, we used else if. This makes the code simpler. When Arduino detects button A is already pressed, it doesn't check button B anymore to find out that it's not pressed, an unnecessary step. It will only check button B when it detects that button A is not pressed. Let's upload this and see if it still works. And that's it for this lesson. Congratulations on completing the first part of your Arduino journey. So far, we've learned how to navigate the Arduino IDE, use Sketch and libraries, and introduce some simple components. In the next lessons, we'll learn more about digital input components like switches and sensors. I'll see you in the next one.